All right. Thanks, Jim. As we said, today's topic is reducing arc flash energies on transformer secondaries, and we're going to talk about 3 fuse solutions. The agenda for today's meeting will start off with a review of this particular application and why it can be troublesome for certain types of fuses. We'll review fuse characteristics, specifically current limitation. We'll talk about how fuses are typically selected, and then we'll go into the 3 different options. The application we'll be discussing today is represented by this one-line diagram. Notice that there's a 1500 kVA transformer that steps the voltage from 13.8 down to 480 volts. Typically, when you see this configuration, the bus shown in red will have an incident energy calculation well over 40 calories per square centimeter. The upper limits identified in FPA 70E. The arcing current shown here, if you notice, is near 40% of the bolted fault current, and that's where the problem is. If we look at the numbers that's specific to this application on the next slide, we'll get some insight as to why it's difficult to get incident energies below 40 with the current limiting fuse on the primary of the transformer. That 1500 kVA transformer has a full load current of 1800 amps on the secondary side, which translates to 63 amps on the primary. With this type of current, a 100E fuse is a typical selection for that. If we look at the available fault currents on the secondary, looking specifically at the switchgear, it's about 29,000 amps, which would be about 1,000 amps on the primary, 10 times the rating of the 100E fuse. The problem comes in is when we looked at this reduced arcing current, it is only 459 amps on the primary. That's less than 5 times the rating of the 100E fuse. That means less than 5 times can be considered to be in the overload region. If you look at the specific curve that was shown on this application, if we look at the 1000 amp bolted fault, clearing times would be under 6 cycles. But now when you look at the arcing current calculations per IEEE 1584, clearing times can range from 3 to 10 seconds. That translates into extremely high incident energies. Just watch this rather familiar video, and when the second worker comes back into the picture, the arc flash will begin, and you'll notice that it's going to be several seconds before it extinguishes. Now, if you counted the time on that, that would be approximately 5 to 7 seconds. Next, we're going to talk about medium voltage fuses for transformers and some of the basics. Current limitation is the primary reason fuses are selected for primary protection. If you notice on this fuse cutaway, there are 4 parallel links that are helically wrapped around a core here. And each link will have near 100 notches, as shown in the little cutout here. These notches have a higher resistance than the rest of the link and will melt first in the presence of a short circuit. So the problem here, if we look at the diagram in the first, when there's a bolted fault on the primary, the voltage that is now imposed on the system is basically the voltage across the fuse. Before these notches melt, that's near 0 volts. So current limitation occurs within the first quarter cycle. As the current's rising, that current flow will cause the notches to heat up to their melting temperature before the rest of the link. When that happens, the notches increase rapidly in resistance as they move from solid material to a gas, to an ionized gas. And if you look at this, on the voltage side, the voltage across the fuse is 0 volts until the resistance increases rapidly and creates a voltage VF that's imposed upon it. When that voltage gets greater than the system voltage, current limitation occurs, and that's shown up here as the current rolls over. Now when this rolls over and you get a negative DIDT, the voltage across the source reactance is added to the source voltage, and you now have a temporary overvoltage until the current clears. This overvoltage is constrained by IEEE standards, and the table is shown here. So for the 15.5 kV class, for the 100E fuse, that voltage cannot be over 49 kV. So what we note here is that until the link melts, could be up to 4 milliseconds, you'll have 0 volts on your system, and then until the fuse clears, that overvoltage will be present. So this will be important in the third solution that we talk about. To give you an idea of why current limitation is important, this is a demonstration of a medium voltage arc flash event in this piece of gear. Upstream from this switch is a 100E fuse, and up in the top of this is a trigger wire connected between A, B, and C phase. So when they close in on this fault, 18,000 amps will begin to flow and melt that wire and create an arc flash. So on the left was the performance with a current limiting 100E fuse, and you can see the limits of the exposure to plasma gases. On the right, within 5 cycles, the entire equipment was exposed to these ionized gases, which are shown by the glowing material on the slide. This is laden with copper, and as such, it will be impregnated and embedded upon a lot of the surface areas within the equipment. So with 5-cycle clearing, you can see the interface barriers now have a lot of copper oxides impregnated them, and you can see it throughout. With the current limiting fuse, where the trigger location was up here, you can see some minor damage, but very little damage on the interface barriers. So this happened in within 2 to 3 milliseconds, limiting the damage tremendously, and hence the downtime. Fuse selection for medium voltage transformers has to be looked at because it really is a limiting factor. 2 of the main things that you have to look at when selecting a fuse for a transformer is the full load current. Fuse must carry it without overheating and opening, but it also must pass the inrush currents for the transformer when you first energize. The fuse must be to the left of the transformer damage curve to ensure that it protects against all through faults and will protect the coils from being damaged. The other thing to be looked at is the E-rated fuse characteristics. You need to match that up with the inrush currents and the damage curves. And to a lesser degree of a limitation is the code requirements. With the electric code, you're allowed to size to fairly large size on these, 250%, which is not a limiting factor. Another thing that may limit your selection would be other protected devices upstream or downstream, and those vary quite a bit from application to application, and that's why you can use EasyPower to solve that. But the basic limitation for fuses for this arc flash phenomena is the limitations on the inrush and full current. So on that example of a 1500 kVA transformer at 13,800 volts, the manufacturer sees 63 amps full load and recommends a minimum sizing of 80 E, but a typical sizing of 100. And when you look at the time current curves, this rough diagram, you'll see the inrush currents are shown here at 0.1 seconds, and fuse manufacturers typically show a point at 25 times. The fuse curve being right to that should pass these inrush currents. You also want this fuse curve to be to the left, to the left of that damage curve. That ensures that you've got adequate protection. So you can see you're really shoehorning this in between 2 points. The 3 solutions that we'll be talking about is first to get a better time current curves for arc faults. The second one will be a commutated fuse approach, And the third is using a high-speed grounding switch in conjunction with the current limiting fuse. Going back to this application, the fuse curve that we had shown was a typical one that's used, and it's as shown on this curve. When you do this calculation, you put that up, you have to use the 85% current calculation for IEEE 1584, and that gives you over 400 calories at 18 inches. If you replace that with a fuse curve that's less inverse and make sure that it passes the inrush currents, you'll find that the clearing times are much faster in this region. For bolted fault currents, it would be near the same. But with these types of substitutions, you can get Category 3 levels of PPE might be appropriate, but it still requires a flash suit. So if you looked at the various options that we'll talk about today, I know Category 0 no longer exists, so I need to update that slide someday. But that's Category 0. Category 2, which is usually people's daily wear of 8 calories or higher, and then when you're above that is a flash suit. So this is normally what would be used for this type of solution. Note that because as you go to larger transformer sizes, you still have the same approximate clearing times. Everything just moves to the right. So with the same clearing times but higher power transformers, that number keeps going up. So the upper limit for that type of approach on 13 kV, 13.8 kV is probably a 2000 kVA transformer. The retrofit solution considerations for this particular solution would be the fact that you would typically be going from a single barrel to a double barrel fuse for this less inverse approach. That would mean you would more than likely need to change your fuse clips, or in some cases just put adders on. So if you had a 9F62 DDD with the standard clips, you can put this addition on and come up with a double barrel clip. The second approach we're going to talk about is a commutated fuse approach, and what is meant by that is you would have your normal size fuse, in this case that we're talking about 100E, and you would have another smaller fuse by ampere rating in parallel to a normally closed contact. Normal current flow would come this way. However, when that contact is opened, now the smaller fuse comes into being. So if you can control this, open this contact during an arc fault event, you can now have the advantage of the clearing time of a smaller fuse. This has been recently introduced where that commutated fuse was put into one body. And we'll talk about that too a little bit. So you can see there's some electronics on here and fiber optic cable, so we'll discuss that in a little bit more detail in the following slides. As I said, the commutated fuse is within this body, so you have a controlled fuse element, a normally closed contact, which is a one-shot device. The device hanging on the bottom is an actuator module, and that is what allows this contact to open. With this approach, you need a relay, typically on the low voltage side, and this relay may be a 50 PAF where you may have arc flash light sensors, or you may have a manual mode switch. What the relay would do is give you a contact closure when there's an arc fault event. That contact closure goes to an interface module which converts the trip signal to a optic signal that's sent to this actuator module. Upon receipt of that, it sends a signal up to this device. Now, the other purpose of the interface module is also to monitor the health of this system, so there's communications that could go back and forth to ensure this is ready to switch. The other function of the actuator module is there are CTs embedded in this fuse as well, and it will block tripping for currents below the ampere rating of this fuse in case there are false trip signals during testing. The two fuse curves are shown here. The main fuse has the traditional shape of the 100E fuse shown below, but the control fuse, as you can see, is down and to the left and can give you faster clearing times. EasyPower Implementation has shown this. Version 9.8 introduced the concept of a relay-controlled fuse group, and within that group is the main fuse, the commutated fuse, the contact, and a relay, actually shown as a switch, and the relay is set to control that switch. So what's shown in this dotted line would be the relay-controlled fuse group. With that approach, you can now move and shape the controlled fuse curve by making different settings on the relay. What's shown with the orange curve here is a pickup that's higher than the pickup of the fuse, and also shows a delay on the instantaneous, so it lifts the curves up and beyond. If this is normal operation, you might consider a maintenance mode switch, in which case you can eliminate those two settings and go to a setting where there's no delay, and in that case the clearing time on these particular ones would give you a value less than 8 calories at 18 inches. This one shows 3.7 at 24 inches. So some analysts run at 24 inch, some run at 18 inches. But the goal of this project was to limit incident energy down below 8 calories per square centimeter at 18 inches. So with this approach, the PPE requirements drop to what's known as Category 2, 8 calories or less with a face shield and balaclava. The retrofit considerations for this approach includes the addition of some equipment on the low voltage side. So in addition to replacing the existing fuses with another fuse that fits into the same 3-inch clips, we have to consider adding CTs if there are none on the low voltage side. We must come up with a relay and in the interface module, as well as a power supply. What's shown here is a maintenance mode keyed switch and a maintenance mode light. And finally, fiber optic cables need to be run from the medium voltage side over to the low voltage interface module. And the third and final solution that we'll talk about for this application is a high-speed grounding switch. In this particular application, it requires an arc flash relay on the low voltage side, a high-speed grounding switch which ties all 3 phases to ground, and then communications between the relay and the switch. Upon sensing an arc flash on the low voltage side, the relay will cause the switch to close within 4 milliseconds. The resultant voltage fault then must be cleared by the current limiting fuses. So therefore it's important that this switch be placed downstream of the fuses. The best way to gain a good understanding of how this system operates is to review the results of a high-power test lab demonstration. In this particular case, we used a 3000 kVA transformer, 1247 to 480. On the left, you'll see the fuse load break switch in which the high-speed grounding switch was inserted. And then the arc flashes were simulated over here in the low voltage switch gear. The 2 tests I'll be showing you were performed in this feeder breaker compartment. The main breaker trip unit was disabled to make sure that the primary side was the primary protection. Modeled in EasyPower, what you see here is with this, we figured there was about 55,000 amps available fault current. With the 175E as the sole protection, the incident energy was well over 400 calories at 18 inches. Note that the primary fault current at 1247 was 36 Ka, well into the current limiting range of 175E fuse. The test configuration chosen in this feeder breaker compartment is very similar to the HCB test configuration being used by the IEEE and FPA collaboration where the horizontal electrodes shown here will electromagnetically eject the arc plasma outward towards the measuring devices or the worker, should that be the case. This was shown to have incident energy measurements twice those of the former IEEE 1584 test configuration where the electrodes were pointing down from the top of the box. So this would have been a worst case simulation. This is from the control room about 100 yards away, and what we see here is a pretty big explosion, and in that case there was no high-speed grounding switch, and the lab shut the test down after 500 milliseconds, well before the fuse could clear. With the high-speed camera, you can see the outward movement of the plasma to the left, but what's also interesting in this is even though the door was open and the plasma is being ejected outward, there was plasma and hot gases visible in the rear of the enclosure, which shows that the plasma was not just electromagnetically ejected, but it thermally expanded throughout the equipment. And when you look at the test details shown here, we're going to compare it with the high-speed grounding switch test, but notice that the arc duration was limited to about 458 milliseconds. The IEEE 1584 calculation called in 27.2, but with this HCB, the actual measured energy was 49.8, showing that this is, in fact, valid prediction by the new equations. Also notice down here on the primary side that the primary current during the arcing fault was 730 amps on average, which is less than what was being predicted by IEEE. So this could give you a double whammy in that respect. This is with a high-speed grounding switch in place, and if you notice, before the gases can be ejected from the equipment, it has been extinguished. And so what we need to do is look at this a little bit closer to see how well this performed. What I'm showing you here is the traces from that last test where the high-speed grounding switch was called upon to open it. The total clearing time on this was less than a half a cycle. What's shown on the top here is the medium voltage traces on one phase, and these are the low voltage traces on one phase. So if you look at the current at red, it starts at point A. And at this point, the current starts to rise rapidly, and the voltage falls to 0. That's because we have not yet melted the trigger wire. At point B, the trigger wire melts, and the arc begins, as evidenced both by the arcing voltage here at the flat top and the decreasing rise of the arcing current. At some point, the switch closed, okay, and this is about 4 milliseconds later, and when that happens, as shown, the voltage on the primary side goes to 0 very rapidly. The current, which was rising to 700 something amps, now rises to the available fault current, which is well over 36 kA. And at point D, the fuse melts. And it was shown earlier, the voltage quickly rises, you have a voltage transient, and at point E, current is out, and now the voltage is back. The time frames here are A to B is the time it took the trigger wire to melt, and the arc flash relay sensed the overcurrent. However, the light sensor did not pick up, so it wasn't until point B that the light sensor triggered the relay to activate the switch. From point B to point C, the duration of the low voltage arc was 1.5 milliseconds, meaning the switch closed in less than its advertised 2 milliseconds. Point C to point D is the duration that you have 0 volts on your power system and have a fast rising current. That lasted 1.1 milliseconds, and at which time the voltage recovered and you had a transient. And then it took another 1.3 milliseconds for that fuse to clear. These are time markers that helped us determine that. There's another time marker over here, 4.0652, that's not related to either of these phases. It has to do with the third phase fuse took longer to clear because of the phase rotation. And now if we look at these side by side, the test on the left was the original test number 9 that had no high-speed switch in it, and it goes on for 450 milliseconds. The one on the right will be the high-speed grounding switch protection. So these slides are the first frames in the high-speed videos where arc light was detected. So this would be the beginning of the arc at point B in the previous trace. 1.5 milliseconds later, you can see the arc gases started to expand, but this is where 1.5 milliseconds is where the grounding switch is now closed, meaning there's 0 volts on the primary of the transformer and the voltage on the secondary is rapidly decaying. 3.6 milliseconds was the duration of the arc on the high-speed grounding switch on the right, and you can see that the gases are no longer expanding and are actually changing colors, meaning they are cooling. In 3.6 milliseconds on the left, you see this plasma hot gas ball being ejected outward and around, so it's being ejected electromagnetically that way, but you can see the expansion going on, and plus expansion into the back of the equipment. In 16.8 milliseconds, the gases have almost cooled completely on the right. You have major involvement of the arc on the left and a lot of arcing going on in the back, not arcing, but gases expanding in there. And note that these gases are laden with copper oxides. You're vaporizing and actually ionizing copper off those electrodes, which are going into this plasma and expanding rapidly. So we're impregnating everything inside this equipment with copper. 32 milliseconds, there's no remnants at all of the arc on the right, and this continues to expand. If we looked into the equipment like we did here and took pictures, with test 5 on the right, the one with the high-speed grounding switch, you can see there's minimal damage due to the arc. Before the arc could be fully developed, it was extinguished. And so this can be repaired in place and put back into service. On the left, with a 450 millisecond clearing time, this equipment is virtually destroyed and would need to be replaced completely. One more thing to look at is the arcing power. We measured it both on the low voltage side and the medium voltage side. So if you look at the blue, this is the power delivered to the arc on the grounding switch, and you see it hits a peak, about 15 megawatts, and then collapses very quickly where the grounding switch closed. But also notice there's some additional energy here under this power that comes from energy stored in the windings of the transformer. So even though the grounding switch has put 0 volts on the primary, there's still energy that needs to be bled off, although it's very little. Thing to note on the primary, the power being delivered is a little greater, but notice these large excursions. That's the arc energy within the medium voltage fuse, and you can see it hits a very, very high level. This would be the first 2 fuses clearing, and this would be that third fuse that cleared. So comparing test 5 to test 2, on the low voltage side, the duration of the arc was less than 4 milliseconds, about 1% of the one on the left. The actual measured energy with the horizontal configuration was approximately a half calorie. That was the highest of all the calorimeters in front of it. The longest under voltage, meaning 0 volts on the medium voltage power system, was 2.4 milliseconds. That's between all 3 fuses. The longest over voltage, while the fuse arc was being extinguished, was 1.5 milliseconds. And its peak voltage was 25 kV, which was well below the 95 kV BIL rating of the equipment. Finally, the thing to note is the arc energies on the low voltage side is 27.6 kWs. And several papers have pointed out that if you're below 100 kWs, Equipment typically can be repaired and put back into service, and there's a small likelihood that the equipment doors will stay closed even on low voltage. The retrofit considerations are very similar to the second. You need a relay on the low voltage side. You need high-speed grounding switches installed, in this case, in the low break switch compartment. They could be installed in compartments on the transformer primary. They just need to be downstream of the current limiting fuses. You need communications between the two and an interface module as well. So if you don't have CTs, they need to be installed. Relay power supply on the secondary side, and fiber optic cables from the low voltage to the medium voltage as well. This solution, the third solution, brings you to what used to be known as Category 0. As it's below 1.2 calories per square centimeter, the requirements for arc-rated PPE is not called for. However, electrical workers still need to be mindful not to wear melting fibers, and they still need their safety glasses, and all the other PPE still require them by NFPA 70 and OSHA. In summary, current limiting fuses provide excellent short circuit protection for the primary of the transformer. However, they have been shown to be somewhat inadequate for protection against arc faults on the secondary of that transformer. What we showed today were 3 fuse options to address this low voltage arc flash issue. The first one involved a less inverse time current curve, which gave clearing times in the 200 to 400 millisecond region that translated for 15 kV equipment to what would be low category 3 type levels from 10 to 20 calories per square centimeter. The second approach, a commutated fuse approach, we showed a new product that had the commutated fuse within the same body as the main fuse. And with this approach, with a relay either in maintenance mode or a arc flash relay on the secondary side, you could get clearing times in less than 100 milliseconds and expect incident energies below the category 2 level of 8.0 calories per square centimeter. And the third and final approach we showed using a medium voltage high-speed grounding switch tied to a secondary arc flash relay using the 50 PAF function with this high-speed switch gave clearing times of less than 4 milliseconds and resulted in incident energies below 1 calories per square centimeter. And we expect those levels to hold for transformers up to 4,000 or 5,000 kVA. Thank you very much. If there are any questions.